For decades, artificial intelligence excelled at a single task: sorting reality. It could look at millions of images and categorize them with superhuman speed. But ask it to create a new image from scratch, and it failed entirely. That barrier recently broke. Neural networks transitioned from merely labeling the world to actively synthesizing it. To understand how, we have to look at two competing mathematical frameworks. The first is the discriminative paradigm. This is an AI system optimized exclusively for predicting labels and drawing strict boundaries between distinct categories of data. The second framework is the generative paradigm. Instead of drawing boundaries, a generative system is designed to map and understand the entire underlying structure and probability distribution of a dataset. These two models approach information from opposite directions. One strips away context to find a dividing line, the other absorbs all available context to reconstruct the whole. The current surge in AI capability stems from a mathematical pivot, shifting computational focus from learning static boundaries toward mapping complete probability distributions. This graph displays a simple two-dimensional feature space populated by blue dots representing dogs and red dots representing cats. A discriminative model's sole job is to figure out exactly where to draw a line between these two groups. In statistics, this is known as learning the conditional probability, maximizing classification accuracy. Once the model finds that boundary, it ignores the actual data points. The generative approach abandons the boundary line entirely. Instead, it maps the actual density and structural relationships of the data points. It learns exactly how the clusters are formed in the first place, treating them as topographical maps of probability. This is estimating the joint probability distribution. By tabulating the exact topographic density of a distribution, the algorithm can sample from it. It picks a valid coordinate within that mathematical shape and outputs a novel data point that never previously existed in the training set. In the 1950s, early artificial intelligence was severely restricted by its hardware. These massive, rudimentary machines confined researchers to simple, rule-based probability models. By the 1980s and 90s, increasing computational power finally allowed for a shift towards statistical machine learning and sequence modeling. This era introduced recurrent neural networks, or RNNs, which became the standard architecture for processing data that follows a temporal structure, like human speech or text. RNNs and later long short-term memory networks operate sequentially. They maintain a memory of previous inputs to generate coherent sequences one step at a time, predicting the next word based on the words immediately preceding it. But this architecture had a strict structural weakness. Linear processing failed when applied to massive, non-sequential arrays of data, like the millions of independent pixels required to form a high-resolution image. Linear memory systems acted as a hard computational bottleneck, effectively preventing the generation of high-dimensional, photorealistic visual outputs. The breakthrough arrived in the 2010s, driven by massive datasets and the parallel processing power of graphic processing units. In 2013, researchers introduced variational autoencoders. These provided a mathematical framework to probabilistically reconstruct inputs by compressing data into a latent representation and then decoding it back out. A year later, generative adversarial networks, or GANs, addressed the image fidelity problem. GANs utilize two separate neural networks locked in a closed competitive loop. The first network is the generator. Its singular objective is to synthesize fake data from random noise. The second network is the discriminator. It analyzes that output, calculates the probability that the data is fake, and sends an error signal back if it catches the forgery. This continuous competition forces the generator to rapidly adapt. To beat the discriminator, it has to perfect its mathematical mapping of the real-world distribution. Shortly after, diffusion models emerged, achieving similar visual quality through a different method, gradually stripping away random static to reveal highly detailed data underneath. Pitting two networks against each other repurposed older technology, turning discriminatory boundaries into an evolutionary pressure for generative creation. In 2017, the transformer architecture provided a departure from sequential processing. Instead of reading data linearly, transformers use an attention mechanism. This allows the network to evaluate the context of an entire dataset simultaneously. By analyzing everything at once, the attention mechanism captures complex, long-range dependencies. that early recurrent networks simply could not hold in memory. When this architecture is scaled across billions of parameters and trained on vast internet corpora, it yields foundation models like GPT and Claude. This sheer scale enables cross-modal synthesis because the model maps the dense underlying relationships across different types of data. A text prompt can now directly manipulate visual and audio structures. By abandoning linear processing for massive, nonlinear context mapping, the architecture achieves the depth required for human-like reasoning and fluency. This underlying theoretical architecture directly dictates exactly how these systems are practically applied in modern enterprise and academic environments. Relying solely on a generative model in a professional setting introduces significant operational risk. Because these models are designed to synthesize probabilistic outputs, they can easily hallucinate facts and reproduce structural biases. To counter this, the most robust software deployments utilize hybrid architectures that combine both historical paradigms. Developers use discriminative classification algorithms as rigid safety guardrails. These classifiers evaluate and filter the raw generative outputs to ensure factual coherence and mitigate fairness issues before the user ever sees them. This hybrid structure directly maps to your own daily workflow. When you practice prompt engineering, you are guiding the model's vast probability distribution. When you critically evaluate its output for accuracy and integrity, you are acting as the human discriminative layer. In the end, true AI mastery involves architecting workflows where strict discriminative logic regulates generative power to produce reliable, unbiased solutions.